Namaste and welcome back to JEE Physics with Typical Monk. This is class 28, Semiconductors. A semiconductor sits quietly between the metal and the insulator, a poor conductor on its own, yet the most powerful material of the modern age. The trick is a small band gap, about 1 electron volt, that a little heat or a little doping can bridge. Add a pinch of impurity and it becomes N-type or P-type. Join the two and a PN junction is born, the diode, the rectifier, the seed of every transistor and chip. Today, energy bands, doping, the PN junction, and how a diode turns alternating current into direct. One idea at a time. Here is what you will master today. First, intrinsic and extrinsic semiconductors. Second, energy bands and the band gap. Third, doping, N-type and P-type. Fourth, the PN junction and the depletion region. And fifth, diode action and rectification, one idea at a time. Let us set the foundation. A semiconductor. It sits between a conductor and an insulator. Silicon and germanium are the classics. The band gap. It is small, about 1 electron volt, and electrons cross it when energized. Doping, adding a trace of impurity to control the conductivity. Master line, the PN junction is the building block of every diode and transistor. Now, look at the picture, the energy bands. The conductor, its valence and conduction bands overlap, there is no gap, so it conducts freely. The semiconductor, a small band gap, about 1 electron volt, electrons jump across when the crystal is heated. The insulator, a large band gap, about 6 electron volts, the electrons simply cannot cross. The band gap, this gap, which we call EG, decides whether a material conducts. Now the difference between pure and doped. Intrinsic, a pure semiconductor. It has equal numbers of electrons and holes, and it is a poor conductor. Conduction. Raising the temperature frees electrons, and each one leaves a hole behind. Extrinsic, a semiconductor doped with an impurity to boost its conductivity. Two types, N-type with extra electrons and P-type with extra holes. Now, the two kinds of doping. N-type, doped with a pentavalent atom, phosphorus or arsenic. It donates an electron, so it is a donor. Its majority carriers, the electrons, and the minority carriers are the holes. P-type, doped with a trivalent atom, boron or aluminium. It accepts an electron, so it is an acceptor. Its majority carriers, the holes, and the minority carriers are the electrons. And both remain electrically neutral overall. Doping does not add charge, only carriers. Now look at the picture, the PN junction. The junction, a P-type region meets an N-type region within a single crystal. The depletion region, near the junction, electrons and holes recombine, leaving behind immobile ions. The barrier. These ions set up a potential barrier which stops any further diffusion of carriers. Biasing. Forward bias lowers the barrier and lets current flow. Reverse bias widens it and blocks the current. Now the diode and how we bias it. The junction diode, a single PN junction, it conducts in one direction only. Forward bias. Connect P to the positive terminal, N to the negative, the barrier lowers and current flows. Reverse bias. Connect P to the negative, N to the positive, the barrier widens and the current is blocked. The characteristic. There is a knee voltage in forward bias and only a tiny leakage current in reverse. Breakdown. A large reverse voltage causes breakdown, which the Zener diode puts to good use. Now, the diode's great job. Rectification. Rectification. Converting alternating current into direct current using the one-way diode. Half wave. A single diode passes only one half of each cycle. Full wave. 2 or 4 diodes pass both halves of the cycle. Now, match each course to its effect. A pentavalent dopant goes to an N-type semiconductor. A trivalent dopant goes to a P-type semiconductor. A small band gap goes to a semiconductor. And forward bias goes to current flows. 4 pairs, each worth memorizing. Now, How many of these statements are correct? Statement 1. In an N-type, electrons are the majority carriers. Correct. Statement 2. A semiconductor has a larger band gap than an insulator. Wrong, its gap is smaller. Statement 3. Forward bias lowers the barrier. Correct. So the answer 2 are correct. Statements 1 and 3. The trap is the band gap in statement 2. Now the two mistakes that quietly cost marks. The truth. A semiconductor has a small band gap, about 1 electron volt, and insulators is large, about 6. The trap. Thinking a doped semiconductor is charged. In fact, it stays electrically neutral. The second truth. Forward bias lowers the barrier and conducts. The second trap. Confusing N-type, a donor with extra electrons, with P-type, an acceptor with extra holes. Now, test yourself. Answer in your head before the reveal. That is how G speed is built. Here we go. Question 1. The band gap of a semiconductor? About 1 electron volt. Question 2. A pentavalent dopant gives? An N-type. Question 3. The majority carriers in a P-type? Holes. Question 4. Forward bias does what to the barrier? It lowers it. And question 5. Converting alternating current to direct. Rectification. Let us gather it all in one breath. A semiconductor, a small band gap, sitting between a conductor and an insulator. Doping N-type is pentavalent, with extra electrons. P-type is trivalent, with extra holes. The p-n junction has a depletion region and a potential barrier. Biasing, forward bias conducts, reverse bias blocks. The diode rectifies alternating current into direct current. Next class, logic gates, and, or, and not. A small gap, a whole industry. The whole of modern electronics rests on one modest fact: a band gap small enough to bridge, warm a pure semiconductor, and electrons cross. Dope it, and you tilt it toward electrons or holes. Press an N-type against a P-type, and a depletion region raises a barrier that lets current pass one way and not the other. That single junction is the diode, and from it flow the rectifier, the transistor, and the chip. Learn the bands, the doping, and the junction, and you hold the foundation of every circuit. Next class, the logic gates. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack G. I will see you in the next class.